Today we are going to solve the problem 559 of Griffith third edition Introduction to Quantum Mechanics. Problem 559 is in example 5.1 and problem 5.5p we ignored the spin, or if you prepare we assumed that the particles are in the same spin state. This problem consists of two parts. Part A is to it part the particle of spin off. Construct the four lowest energy configurations and specify the energies and degeneracies. So now we can see this is the expression given in example 5.1. Example 5.1. So this is the wave function and this is energy level, energy state, nth state energy level, where k is, we know the k is pi squared, k is equal to pi squared h cross squared over 2ma squared. Now we can use the Dirac notation to uh, define a get vector, that is which contains this spin quantum number and magnetic quantum number. S is the spin quantum number, M is the magnetic quantum number. So the wave function we can separate it to two parts. One is radial part of the wave function, other one is spin part of wave function. The radial part of wave function is psi of x and the spin part is chi of s. So for Permian, we know it is anti-symmetric. So if it is anti-symmetric, mean either either one of this is symmetric. Either psi of x will be symmetry and chi of s is anti-symmetry. So if psi of x is anti-symmetry, then naturally the chi of s is symmetry. Any one of this one is symmetry and the other one is anti-symmetry. For the case of symmetric wave function, both must be symmetric or both must be anti-symmetric. With this understanding, we will move further. Now let us take the simplest case of spin of particle. So total spin, two-level system, if you take, if two-state total spin is one, we know, because two particle, one, and magnetic quantum number is zero. So this can be written as linear combination of two states. That is 1 over square root of 2 spin up and spin down. So total spin is zero in this case. Here spin down and spin up with the negative sign. If you swap the spin state, what will happen? If you swap both, then sign will get changed. So naturally this will be anti-symmetric. In that case, the radial part of the wave function must be symmetric. So this state is called singlet state. This is a singlet state. Then we will move on. That is spin is 1 and magnetic quantum number is 1. That means both particle will be in spin up state. And see if S is equal to 1, then M must be equal to, maybe I will use different color, 2S plus 1. So if S is equal to 1, then M will be 3. So 3 means it start from minus S and end with plus S. So here 1, if you reduce 1 by 1, 0, then minus 1. So you have 3 state. Since S is equal to 1, M is equal to 2 S plus 1, 3. So 1, 0, minus 1. So this magnetic quantum number is 1 only when both particles are spin up state. Then if then next state is 1 0. So you can take square root of 1 over square root of 2 spin up spin down plus spin down spin up. Here even if you swap the particle, uh, this will become spin down spin up. This will be spin up, spin down. So nothing will change. So it is a symmetrical one. Similarly, uh, 1 minus 1, both are down. In this case also, if you swap the particle, you will not, it will not change the state like here. So with this understanding, we will move on. Before that, I like to label it as triplet state. This state, these three states are called triplet state. So with this understanding, we will move further. Now we will see the energy and degeneracy. If particles are distinguishable, then ground state is psi 11 get s comma m. So in this case, you have one singlet state and one triplet state. Singlet state is, as we see, it is anti-symmetric. I simply write A anti-symmetric, and this is a symmetrical one. So the wave function must be opposite. That is, for singlet state, this is uh, symmetry. So that total product will be anti-symmetry. For triplet, this wave function must be a anti-symmetry. So that this triplet state we have seen is a symmetry. Now you know that both particle will have same energy, k plus k, because both are having the ground state energy. K is the ground state energy. Then what about total energy? K plus k is 2k. This is then about degeneracy. There is one singlet and one triplet. So totally four degeneracies four. Then what about first excited state? First excited state is psi 1 2 multiplied by get s comma m or psi 2 1 s comma n. Here also one singlet and one triplet. But this is state we can distinguish the difference between psi 1 2 and psi 2 1. So here you have four state, one singlet and one triplet. Here also one singlet, one triplet. That is 4 plus 4, 8. So degeneracy is 8. What about the energy? Energy is 1 squared plus 2 squared. Because one is at ground state, one is at first excited state, which is equal to 5. So it is 5k. So degeneracy is 8. What about second excited state? Is psi 2 to uh, get s comma m, which is equal to here you will have one singlet and one triplet state. Then total energy 2 squared plus 2 squared is 4 plus 4 8k. And what about degeneracy? Degeneracy is one singlet plus one triplet, 4 energy state. Then what about the third excited state? Third excited state is psi 13 get Sm or psi 31 get Sm. Remember that there is since it is distinguishable, you can distinguish psi 13 from psi 31. So you have here for one singlet, one triplet state. Here one singlet, one triplet state. So totally degeneracy is 8. Then what about the energy? 1 squared plus 3 squared. 1 squared plus 3 squared. 1 plus 9 is equal to 10. So 10k. Now we will move on to the identical particle. Now we will see the same thing for identical particle. For the ground state, psi 11 get Sm. So this is a symmetrical one because both particles are at ground state. So naturally, since it's a symmetry, it must be anti-symmetry. We have seen if it is anti-symmetry, is a singlet state. So naturally, the degeneracy is 1. What about energy? Energy is 1k plus 1k because this energy is multiplicative. Wave function is product. So k plus k, you will get 2k. Then what about the first excited state? First excited state is psi 1 to s comma m get s comma m or psi 2 1 get s comma m. But is a identical particle. There is no difference between psi 1 2 or psi 2 1. Both are same because it's identical. Then what about the get vector Sm? Sm will have 4 states, one singlet and one triplet. So degeneracy is 4. Then what about energy? Energy is 1 squared plus 2 squared. 1 squared plus 2 squared, which is equal to 5. So 5k. Then what about second excited state? This psi 2 2. Both the particles are at same energy level. So naturally it's a symmetry. Then it will be anti-symmetry. That means singlet. So degeneracy is 1. What about energy? 2 square plus 2 square, which is equal to 8. So 8k you are getting. Then we will move on to a third excited state. That is psi 1 3 get SM or psi 31 get SM. So we know psi 13 and psi 31 are the same because identical particle. Then the degeneracy is one singlet and one triplet. Degeneracy is 4 and the energy is 1 squared plus 3 squared, which is equal to 10. So this will be 10. Thank you very much. Since it's a lengthy problem, I have split it into two parts. Part 2 we will see in the next class. Thank you very much for watching my video and supporting me continuously. Thank you very much.